morning, good afternoon, and good evening, whichever time zone you are in. Today, I'll be talking about learning to combine instructions in LLVM compiler. This is a work in progress where we try to apply neural networks and machine learning to the instruction combining paths in LLVM compiler. So this is a work done jointly with Dr. Dibyendu and I am Sandya Mannarswamy, and we are both part of the AI compilers group in Intel India. As you know, instruction combiner is a basic and critical optimization path in all compilers. Instruction combiner, or IC as it is known, tries to replace a sequence of instructions with an equivalent and optimized instruction sequence at the basic block level. Essentially, what it does is it takes the incoming instruction sequence and tries to match it against a set of pattern matching rules. And once a match is found, the corresponding target sequence is replaced for the source instruction sequence in that basic block. And there can be thousands of such instruction combining patterns. And these patterns need to be frequently updated over time as software evolves, applications change, and with newer hardware as well. Therefore, there is high software maintenance cost that's associated with the instruction combiner path. And prior work has shown that IC is the most frequently updated component in the LLVM compiler. Given this considerable human effort, high software maintenance cost, and of course the software complexity, we explore the question whether it is possible to replace or augment the traditional instruction combiner with a machine learned model. So how do we try to do this? We want to replace the pattern matching part of the instruction combiner with a machine learnable IC path, and we try to model this as a machine translation task. Neural machine translation actually translates from a source to a target language. For instance, if you're given a sentence in French, it can do a corresponding translation to a target language, say English, using a neural network, and this is known as neural machine translation. In our case, the source and the target language, both of them are LLVM instruction intermediate representation. So we model this instruction combining path as a neural machine translation task, where the source language is unoptimized instruction sequence in LLVM IR, and the target sequence is optimized instruction sequence in LLVM IR. And we try to leverage sequence-to-sequence models, which are state-of-the-art models for neural machine translation tasks, and we use them for learning to combine instructions in the LLVM compiler. And we talk more about this in subsequent section of this talk. Before we get to how we implement our machine learned model for instruction combiner, there are a number of design choices when we are trying to use a neural instruction combiner. So the questions are, what would be the input representation for our sequence-to-sequence model? And if you want to use machine learning, where can we find a data set for learning this model? Or how can we build a data set for learning this model? Once we have built a machine learned IC model, how do we integrate into the overall LLVM optimizer pipeline? Given that the machine learned model would generate a probabilistic target sequence, how do we validate the IR generated from the neural instruction combiner? So to give you a high-level perspective of the neural instruction combiner, NIC, or neural instruction combiner, has three major components. The first is the NIC inputter. This is a non-ML module. This creates an encoded distilled representation from the LLVM IR instruction sequence corresponding to a basic block. The reason we do this is, the standard LLVM IR instruction contains a number of items which are not really needed for the instruction combiner. The instruction combiner is typically concerned with the opcode of the instruction, the type of the operands, and the operands themselves, right? It is not very much interested in the instruction completers or and in some cases in the debug information or the metadata associated with an instruction. So we want to remove this extraneous information so as to make the translation task easier. And therefore, the NIC inputter takes the standard unoptimized LLVM IR instruction sequence and tries to create an encoded distilled representation corresponding to the sequence for a basic block. The output from the NIC inputter is then fed to a module called NIC Converter. This is actually a machine learned model. As I said, we use a sequence-to-sequence neural network model for this task. It takes the output from the NIC inputter and it generates an equivalent optimized encoded instruction sequence. Now, this encoded optimized instruction sequence from the NIC converter output is fed to another module called NIC outputter. This is again a non-ML compiler module. It converts the NIC converter output back to full-fledged LLVM IR instruction sequence of a basic block. Remember, we created an encoded representation at the NIC inputter, and we want to now take this optimized encoded representation from the NIC converter output and then convert it back to the full-fledged LLVM IR instruction sequence, which is optimized corresponding to that basic block. The NIC outputter also does a number of IR verification checks and verifies the validity of the translation so as to ensure that the generated translation is semantically equivalent to the source instruction sequence. And we do this using an external translation validity tool called Alive2. So these are the three major building blocks for the neural instruction combiner, and we'll talk more about them subsequently. This before, we use sequence-to-sequence model in our NIC converter for translating from unoptimized IR instruction sequence to an optimized IR instruction sequence, modeling this as a monolingual machine translation task. So we want to provide a brief overview of the sequence-to-sequence model. As you know, these are highly popular models used for machine translation in natural language processing. A sequence-to-sequence model take a source sequence, pass it through an encoder, which creates a fixed length compressed representation of the source sentence. This encoder output is then fed to a decoder block, and the decoder actually generates a target sequence one token at a time using this context vector and the previously generated token by the decoder. So let's say if you're trying to translate from English to French, your source sentence is actually in this case, we have French to English. So if you're trying to translate a sentence from source sentence French to your target sentence in English, you're going to take the source sentence and feed it as token embeddings to the encoder. The encoder produces output for each of these tokens, and the last stage encoder output is taken and fed as a context vector to the decoder. Now the decoder takes this context vector and the previously generated output from the decoder and produces a next decoder symbol. Now, as you know, the encoder and decoder blocks are the two major part of the sequence-to-sequence model. If you think about it, the decoder actually generates the next token in the target sequence, one token at a time. So this is very much similar to a standard language model in natural language processing. However, this language model decoder is actually conditioned on the encoder output. So we can treat the decoder as a conditioned language model, which generates a target sequence one token at a time based on the output from the encoder. And as I said, the decoder would generate the output token based on the encoder context vector and the previously generated token from the decoder. During training, we use teacher forcing, which means that we use the previous symbol from the ground truth translation for that sentence. Whereas here what we are showing is the test time behavior of the decoder. So the actual symbol which is generated by the decoder in the previous step is fed to the next stage of the decoder. So it would use the actual output of the decoded symbol in the previous stage and the context vector to produce the current decoded output symbol. And this happens one token at a time. As you know, vanilla sequence-to-sequence model consists of an encoder and a decoded block, and the context vector for the decoder comes from the last stage output of the encoder. However, this leads to what is known as a bottleneck problem. If you have a long sentence, the encoder tries to compress all the information in the sentence into a single fixed length context vector, and this can result in loss of information to the decoder. To avoid this, sequence-to-sequence models have what is known as an attention mechanism. And attention mechanism allows the decoder to look at specific parts of the source sentence when it generates each of its output tokens. This is done by combining all the encoder outputs, not just the last stage of the encoder output. We take the output from every stage of the encoder and create a weighted combination of these outputs and create a context vector, right? This context vector is then fed to the decoder, and at each step, like, we use the attention weight to modulate what parts of the input sentence that the decoder will look at as it generates the output symbol. And the attention weights are actually learned as part of our training the sequence-to-sequence model. And we will talk a little bit more about this, in the subsequent slide. Here we have an example of a sequence-to-sequence model with attention. So what's the difference between a vanilla sequence-to-sequence model and a sequence-to-sequence model with attention? Is basically that instead of having a single context vector, which is the last output of the encoder, we create a weighted combination of each of the encoder output and feed it as a context vector to the decoder. Right, and the encoder blocks and the decoder blocks can either be RNN, that is the recurrent neural network, LSTM, long short-term memory network, or they can be a transformer block. So we'll see what each of these are next. Right, to put things back in context, so far we have been talking about sequence-to-sequence model, and we were not really talking about the neural instruction combiner. So if you recall, neural instruction combiner has three building blocks: the inputter, the NIC converter, and the NIC outputter. So the NIC converter is where we use these sequence-to-sequence models. We use two variants. One is the recurrent neural network based and another is the transformer based. So here is an example of the recurrent neural network based NIC converter module. This, as I said, the RNN blocks are actually long short-term memory network, or LSTM. So you would see a sequence of LSTM cells in the encoder. Similarly, you would see a sequence of LSTM cells in the decoder, and we have the attention block. The encoder has stacked the layers of LSTM cells, and these are bidirectional. So you get the context in the encoder from both left to right and right to left. So it's a bidirectional LSTM layer stacked. In the decoder, since we are actually generating the target sequence one symbol at a time, it's unidirectional. Again, you have like a stacked LSTM layers, and basically this is followed by a softmax layer. And we talked about attention mechanism. Attention creates a weighted combination of the encoder outputs to feed it a context vector to the decoder. And the attention weights are themselves learned during the training process. Typically, the attention block consists of a feed-forward layer followed by a softmax. And that is how we get the attention weights. And these attention weights would then be used to construct the context vector for the decoder. Right? Now, let's look at how an NIC converter, which is transformer based. This is pretty much similar to the RNN based model, except that instead of an LSTM layer, now we will have transformer blocks. And these blocks would also be stacked in the encoder and the decoder. So what does a transformer block in an encoder consist of? It consists of like two sublayers. One is what is known as multi-head attention, and another is like a feed-forward layer. And these are followed by what is known as a layer norm. So we talked about attention earlier, and the attention we talked about is what is known as typically as cross attention. the attention between encoder and decoder. However, what transformer deploys is what is known as a self-attention, where you compute exactly the same attention mechanism, but you apply it on the same sequence. So if you have a source sentence, you compute attention across different tokens of the source sequence itself. In the RNN model, we were looking at cross attention, where we were computing attention between the source sentence and the target sentence. In transformer block, we use self-attention mechanism, where we compute attention between different parts of the source sentence itself. So the transformer block in the encoder would consist of a self-attention module, which is multi-head attention. And you also have like a followed by a feed-forward neural network, pointwise feed-forward neural network. And each of these layers are followed by what is known as a layer norm. And this is a standard transformer block, which is used for various sequence-to-sequence models like a neural machine translation and so on. And the transformer block also has what is known as positional encoding. Remember, when the input source sentence comes, we create token embeddings for the input sequence. We also want to know at what position each of the tokens appears, basically the relative position of one token from another. So we also, in addition to the word embeddings, we also have the token or positional embeddings of the source tokens. So these are fed as input to the encoded block. And between the encoder and the decoder block is pretty much similar to the encoded block. Again, you have self-attention and followed by a feed-forward neural network. And each of these sublayers have a layer norm associated with it, and these are all stacked. In addition to the self-attention mechanism, in the decoder, we have a cross-attention from the encoder to decoder, similar to the way we had in the RNN model. And these are very standard sequence-to-sequence model. It's just that in our case, instead of a translation from a source language, say French, like your target language English, in our case, we employ it for monolingual machine translation. The source is unoptimized IR instruction sequence corresponding to a basic block. The target is optimized IR instruction sequence corresponding to a basic block. Now let's look at how we train the NIC converter. We have source file at the LLVM front end. This passes to the standard optimizer pipeline. At the input to the traditional instruction combiner, we have the unoptimized IR corresponding to each basic block. Now we take this IR corresponding to each basic block, pass it through the NIC inputter, get an encoded representation that becomes the source sentence. Similarly, we tap the output at the traditional instruction combiner corresponding to each basic block, pass it through the NIC inputter, and this becomes the target sentence. So the source sentence is the encoded representation of the unoptimized IR at the input to the traditional instruction combiner. And the target sentence is the optimized IR at the output of the traditional IC. And this becomes our data set, our training data, which is then passed to the sequence-to-sequence model to train it as a neural machine translation task. Remember, we are trying to learn this in a supervised manner. And the policy we use is behavioral cloning, which is basically we try to mimic the behavior for the traditional instruction combiner. And how do we actually deploy the neural instruction combiner in the optimizer pipeline? Once we have a trained model for the NIC converter, we deploy it in inference mode in the optimizer. So in the optimization path, that is a non-training path, we have, instead of the traditional instruction combiner, we replace it with a neural instruction combiner component. So the unoptimized IR corresponding to each basic block comes to the neural instruction combiner, goes through the NIC inputter, which creates an encoded representation, passes it through the NIC converter model deployed in inference mode. So this would predict a target sequence corresponding to the source sequence from the NIC inputter. And this is the optimized encoded IR sequence at the output of the NIC converter. It is then passed to the NIC outputter. NIC outputter takes two input. One is the source basic block instruction sequence and this optimized encoded IR output from the NIC converter. and it recreates a full-fledged LLVM IR sequence, which is optimized. It also does one more thing. Given that NIC Converter probabilistically generates the target sequence, since it's a machine learning model, we need to verify that the generated sequence is valid. So the NIC outputter does compiler IR verification checks, a CFC validity check, and then it invokes an external translation validity tool, Alive2, to verify that the translated IR sequence is semantically equivalent to the source basic block sequence. If Alive2 detects any of the flags, any of the generated sequence as invalid, then NIC outputter marks it as invalid, and it just copies the original unoptimized source basic block sequence as it is like to the output of the instruction combiner. So essentially this particular basic block, if it was marked invalid by Alive2, we will only get the unoptimized IR sequence and it won't be optimized by the neural instruction combiner. So this would end up leaving optimization on the table. Next is we talked about general attention mechanism in the context of a sequence-to-sequence model. We also introduced a novel compiler-guided attention mechanism. Compiler-guided attention is basically to use the alignment information available with the compiler, in the sense that the compiler knows what tokens in the target instruction sequence map to what tokens in the source instruction sequence. Using this information during training data generation, we create a compiler-guided attention matrix. The compiler-guided attention matrix terms are fixed attention scores provided by the compiler. They are not modified during training. So what we do is that we force the learned attention weights to be closer to the compiler-guided attention matrix. And this is done by introducing an additional loss objective to the decoder. So now the decoder, in addition to the standard token level loss objective, we also have a compiler guided attention mismatch loss. This would force the learned attention weights to be closer to the compiler guided attention matrix weight during the training process. And we do not deploy compiler guided attention during inference because the learned attention weights themselves would be encoding the information which was available through the token alignment the compiler had. And we report results for compiler-guided attention in later slides. So coming to experimental evaluation, since there are no ready-made datasets available for this problem, we created our own dataset using two sources. One is the LLVM application test suite and another is the ANGA bench. And we trained the NIC sequence-to-sequence model using the standard mini-batch gradient design with cross entropy loss and Adam optimizer, and then we deploy the trained model in an inference mode in the optimizer pipeline and evaluate with the test dataset. As I said, we have two major variants for our NIC converter. One is based on LSTM RNN blocks, and other is based on the transformer block. And we experiment with different hyperparameters for the transformer in terms of number of layers, embedding dimension, number of heads, and so on. And we also consider both standard attention mechanism and compiler guided attention mechanism. And in terms of the model performance metrics, we report two things. We use a standard machine translation metrics such as Bleu and route scores. And these are for reporting on the translation quality. Basically, we have human translation. In our case, the ground truth would be what the traditional instruction combiner would have been emitting. And we compare what NIC converter generates to the traditional instruction combiner and report the Bleu and route score. As you know, Bleu and route score are evaluated at multiple n-gram level, unigram, bigram, up to L-gram level. And we combine all of them and they are traditionally reported as a single final score to evaluate neural machine translation system. However, our case, since this is a compiler optimization task, we also have a task specific metric, which is actually the exact match comparison result. So we report on the exact match comparison between the predicted sequence and our ground truth. And we report this separately for optimized and unoptimized sequences. When we look at experimental results, as I said, we report for a bunch of variants from LSTM models to transformer model. We find that the transformer models outperform the LSTM based model by 2 to 3%. Even in the transformer model, introducing positional encodings was not very useful. We find that, for the unoptimized sequence, the transformer models are able to reach exact match accuracy of around 0.93 or 0.94, which is very good because they have high fidelity. But in the case of optimized sequence, we reach an exact match percentage of only 0.72 with the transformer model, which means there is considerable performance being left on the table by the neural instruction combiner, because these would be unoptimized and they would be like performance which is getting left on the table. We also find that compiler guided attention improves performance in the case of an LSTM model by 2%, but it did not have significant impact for the transformer based models. In order to understand what kind of mistakes the neural instruction combiner makes, we looked at the error analysis of the neural instruction combiner by analyzing the outputs from the NIC converter. We find that actually the NIC correctly fixes up the uses of a particular opcode. Basically, the operands, like when an instruction gets replaced, the uses of the instruction are also updated correctly. However, it makes mistakes in generating correct values for synthesized constant, in particular for get element pointer and allocate. Get element pointer is a frequently used instruction in LLVM IR, and this is used to get the address of a sub-element in an aggregate data structure such as a struct or an array. And you could see a sequence of get element operation when there are nested data structures, nested structs, and so on. So instruction combiner actually does an optimization to coalesce these get element pointer operation and generate a single get element pointer. So NIC actually makes mistake when it tries to synthesize these get element pointer constant, and it ends up reproducing the memorized frequent constant value, which is a problem. So this is something which needs to be addressed in future. In terms of related work, similar in spirit and complementary to our approach is a work on building super optimizers. This is from 2006, Building Super Optimizers for Binaries by Saurabh Bansal and others. And this has been extended over recent years in improving the search space complexity. They basically build a database of possible optimized sequences from the binaries. The high overheads exist due to the huge candidate search space, and recent work has tried to mitigate this by using stochastic search and reinforcement learning based techniques. As we mentioned before, our work is currently a work in progress. So there are a number of open issues and challenges that need to be addressed. One is that we realize only 72% of the optimization opportunities by neural instruction combiner. This leaves considerable performance potential on the table. We also are interested in exploring scalable translational validity checking for the NIC generated code sequences. And we also want to look at expanding the dataset for training NIC. Currently, we use supervised learning in terms of behavioral cloning the traditional IC. An alternative approach would be to use reinforcement learning based technique to explore the search space of optimized instruction sequence. And we plan to follow this up as part of our future work. Thank you.
All right. Thank you very much for the presentation, Sandya. We are a couple of minutes after the time, but I think we can take a couple of questions since we are now on break. I do see a question on the chat. Parmit, do you want to speak up or do you want me to read it out loud?
Thanks, Jose. I can speak up here. So, Sandya, thanks for sharing this amazing work. My question is more with respect to like how efficient is this model in identifying new patterns, like which were not existing in the training data set that was already being used?
Yeah, thanks, Pamit. That's why, I mean, right now, like, it's not efficient, like, in generating new patterns, in the sense that it's not going to synthesize like new optimization sequences, which is not learned by the traditional IC. The reason is that we are like doing behavior cloning, and are basically like the model will not be extrapolating. At least we didn't find anything like cases where like the model was able to learn new optimization sequence which are not part of the traditional IC. And that's one of the reason we want to move away from like the supervised learning approach, where we are doing this behavioral cloning, and go into an RL model. So right now, like, we don't expand this like a newer set of, I mean, finding newer optimization sequences other than what is there in traditional IC.
Yep, sounds good. Thank you. Thanks, Sandya.
We also have Ajay hands raised. So go ahead, Ajay.
Yeah, thanks. So just a quick question on the code generation itself. You mentioned that currently the approach you're taking to generate, I guess the target IR is, just essentially make a language model, or essentially use a decoder to generate some IR and then check if that's correct. Do you think it would be worth, I don't know, considering approaches that generate, I guess structurally, a different type of architecture that is designed to generate valid IR by design, or is that sort of not a big bottleneck currently?
Right. So, I mean, because we are following, I mean, we decided to go with a mission translation kind of approach where we don't have a constraint specifically, right? I mean, we are using supervised learning, and we use a standard decoder model, like where only we are conditioning on like the encoder output, right? So we don't have a way of constraining on the correctness of the basically the translation. Because we use a standard like mission translation task. So that is another reason like we want to consider an oral approach where like you constrain in your cost model two things. One is like, I mean, how much is the performance of the reward by doing the optimization, and other constraint would be the translational validity. Right now that is not part of it, and that's the reason we end up like using an external validity checker.
I see, but do you think these constraints would like improve the performance? So, like, for example, like how often does the decoder generate invalid code?
Right. We actually haven't measured it yet. How many times, like, I mean, in case of our test data set, we are ending up like hallucinating and not having a valid translation. But your point is right. Like, I mean, it's not going to, I mean, it will not, I mean, it will not improve the performance in terms of like, let me step back. Actually, it will improve the performance in the sense that, like, I mean, if it's actually generating valid code, we are not going to end up like dropping the output from the NIC outputter. So you are correct from that perspective, but that's not something we have yet measured.
Okay, I see. Thank you.